Okay, let's continue. So I'll breeze through major trends affecting main memory just to, again, warm you up. But basically, we've covered this yesterday, right? There are three major trends. One is main memory capacity, bandwidth, and quality of service. The need for this is increasing, and there were many reasons for this. Multi-core, we're increasingly adding more cores. Applications are increasingly data intensive, and we're consolidating more and more, or we should be consolidating more and more on chip. The second, energy and power is a key system design concern, and we will see this even more in this lecture. And third, DRAM technology scaling is ending. And ending may be a strong word, but it's becoming much more costly going into the future. And this, again, to jog your memory, we were talking about this DRAM scaling problem. It's very difficult to scale the size of the cell because it becomes unreliable and leaky. As a result, the refresh rate needs to increase potentially. So there are two potential solutions that we're going to examine. One is tolerating DRAM by taking a fresh look at it, and that's the subject of today. So hopefully we'll cover several techniques that are exciting to me. The second is enabling emerging technologies, and that will be tomorrow. And we'll try to do both, design hybrid memory systems. So what is the first approach? We'd like to overcome these DRAM shortcomings by rethinking DRAM. Again, as I said yesterday, DRAM has been a dumb device. It basically responds to commands. It has all those timing constraints that need to be controlled. It doesn't do anything beyond that, right? So we'd like to design the system together with the DRAM and look at new DRAM architectures, interface and functions, and do better waste management. And these were the key issues to tackle: refresh energy, improving bandwidth and latency, reducing waste, and enabling reliability at low cost. I won't be able to cover all of these, but I'll be able to hopefully talk about reducing refresh energy, maybe reducing waste a little bit also, and improving bandwidth and latency. So let's see where we can get today. Okay, so I'll talk about four different DRAM architectures which can actually be combined together. First, let's tackle the refresh problem, because this is, I think, one of the biggest problems going into the future. Again, just to remind you, DRAM capacitor charge leaks over time. As a result, the memory controller needs to refresh each row periodically so that you can maintain data integrity. And what is a refresh? Basically, you need to activate and pre-charge the row every n milliseconds. Today, typical n is 64 milliseconds. Every 64 milliseconds, every row in DRAM needs to be refreshed. There are many downsides of this that we covered. This consumes energy. This reduces performance because when you're trying to access DRAM bank, you cannot access it. In fact, the DRAM rank, you cannot access it today in commodity DRAM. Quality of service impact, you get pause times during refresh. And the refresh rate actually limits DRAM density scaling. Let me briefly tell you, this won't give you much information, but basically today, what happens with the refresh is the DRAM controller periodically sends auto-refresh commands to DRAM, in fact to a DRAM rank. And a batch, DRAM itself, the DRAM chip itself, refreshes a batch of rows periodically with this auto-refresh command. That's how it is. This didn't used to be the case previously. Previously, the function, you had a mechanism in the memory controller that could refresh individual row. You could actually send a refresh command to each row. But today, DRAM chips have this function, which is not necessarily a bad thing. But what is the overhead of this in terms of performance? So we've done the scaling study. This is device capacity on the x-axis from 2 gigabit chips to 64 gigabit chips. And the y-axis shows the percentage of time the device spends refreshing. If you look at today, this is present, and this is the future. We don't have 16 gigabit chips yet. But with a 4 gigabit device, the device spends 8% of its time refreshing, which may not be too bad. It's still a waste, right? With a 64 gigabit chip, we expect that it's going to be 46%. So half of your time will be spent refreshing. And this is the scaling trend over past generations. And you could argue with the numbers. In fact, many people argued with the numbers, and that's okay. But the trend remains the same. The trend is actually exponential. So we'd like to solve this problem. The second, what about the impact on energy? Again, device capacity on the x-axis and percentage of DRAM energy spent refreshing on the y-axis. With today's DRAM chips, you get 15% of the time, 15% of the DRAM energy spent refreshing. In the future, it'll be almost 50% with a 64 gigabit DRAM chip, if you want to scale the size of the chip. Well, why does this happen? Well, there are many reasons. You increase the number of rows, right? That's one reason. The second is you actually make your transistors more leaky going forward into the future. As a result, you may need to increase refresh rate. That's why the scaling trend is there. So we'd like to solve this problem. We don't want a device that's not very efficient. So there's one problem with conventional refresh. Every row is refreshed at the same rate. So this has been observed. This is some data that shows what happens if you actually change the refresh interval in DRAM. Basically, if you reduce the refresh rate. Basically, the observation other people have made also is most rows can be refreshed much less often without losing data. And this graph shows one example. This is what happens as you increase the refresh interval from, I believe, 64 milliseconds, every 64 milliseconds, all the way to, I guess this is 10,000 seconds. Yeah. And this shows the failure probability of a cell because it cannot retain data. And if you look at here, this is the number of cells in a 32 gigabyte DRAM system that fail. So if you increase the refresh interval to 256 milliseconds, you get only about 1,000 cells fail. So we've quadrupled divided the refresh rate by 1/4, by 4, but we don't get a lot of failures. And that's the observation. Most DRAM cells can actually retain data for much longer than 64 milliseconds. And why does this happen? Because there's a lot of process variation. You cannot manufacture DRAM perfectly. When you manufacture, these capacitors and access transistors are all different from each other. And because of the process variation, you see significant differences. In fact, we've done this experiment on real commodity DRAM chips today, and we see the same curve in existing chips. Yes? Yeah, we'll cover that. And that's already done today in today's systems. As temperature increases, memory controllers adapt the refresh rate. But that's a very predictable predictable thing. So you can actually adapt the refresh rate nicely. Okay, so that's the observation. Let's zoom into, the problem is there's no support in DRAM for different refresh rates per row today. So let's zoom into this curve a little bit. If you look at this curve is also exponential, right? As you increase the refresh interval from 64 milliseconds to 128 milliseconds, only about 30 cells fail in a 32 gigabyte DRAM system. And as you increase it more cells starts failing. So the observation is that only very few rows need to be refreshed at the worst case rate. And it turns out actually these cells are relatively randomly distributed across the DRAM chip. So you could think that 30 rows fail as you increase the refresh interval to 128 milliseconds. So basically the question is, can we exploit this to reduce refresh operations at low cost? And that's what we're going to do. One idea could be, I'll get that later. Yes, very quickly.
So are these rows constant during time? We know that this row always needs to be refreshed faster? Or?
If you can identify them correctly, yes, they're constant, as far as we know. So if you can identify the worst case retention time for each row, then they're constant. They don't change over time. And temperature has a predictable effect. Well, we can discuss that in more detail. There's a lot of interesting things there. How do you identify them is a very interesting topic. So the idea is to identify the retention time of these different rows and refresh each row at the frequency it needs to be refreshed at. Right? It's a nice idea, I think. The problem is if you do it per row basis, it's not a very cost-conscious idea, right? There are a lot of rows in DRAM. We've done that calculation yesterday. It was more than 16 million rows, right? And where do you store this information? If you store it in the DRAM chip, it's expensive. If you store it in the memory controller, it's expensive. And not scalable, too. So a more cost-conscious idea is to bin the rows according to their minimum retention times and refresh rows in each bin at the frequency, at the refresh rates specified for the bin. And what works in our favor is the shape of the curve. If you look at the shape of the curve, basically only very few rows need to be refreshed very frequently, which means that you can have only a few bins. Only a couple of bins, actually, can enable you to refresh rate significantly. So you can have very little overhead to achieve large reductions in refresh operations because you need to store the addresses of only very few rows, less than 1,000 rows in those bins, so that you can refresh some rows at 64 milliseconds, some other rows at 128 milliseconds, some other rows at 256 milliseconds. And maybe you refresh everything else at 256 milliseconds. So that's the idea in this paper. So how does this work, the mechanism? First, you have to figure out the retention time, how long a row can retain data for all DRAM rows. And this is important, and there are challenges related to this that I will not talk about. Well, I may be able to talk about it if we have time, but it's very unlikely that we'll have time at the end of this lecture. And this can be done at DRAM design time or dynamically. Yes?
What is the retention time
So you have to identify those rows that such that you have to get the minimum retention time. Yes, and there are phenomena in DRAM where you actually the retention time changes over time, but you have to find the worst case retention time over time. But as far as we know, as far as today, the DRAM doesn't necessarily age. So aging, as far as we know, aging does not change the retention time. But there's a phenomenon called variable retention time in DRAM, where a row stays in a high retention time state for a while and then goes into a low retention time state. So you have to discover that low retention time state. And that's a challenge actually in profiling. But DRAM manufacturers actually extensively profile their chips. They can expose this information, but there are some challenges related to that too. But I will not go into the challenges. Take this, assume that this is a given, but if you're interested in doing research in this area, this is a very interesting research area also. Assume that this is a given for now. We know the retention times. Once you know that, you can store the rows into bins by retention time. And we're going to use Bloom filters for efficient and scalable storage. We're not going to associate retention time for every single row because that's extremely expensive. So if you look at DRAM visually, this is what it looks like. And if you profile the retention time, this is what you see. There are a few rows that have retention time between 64 to 128 milliseconds. There are some others between 128 to 256, and everything else is greater than 256. So you can actually have only two bins. You can store the addresses of this and this. And that's the idea. And if you do that in Bloom filters, you get only 1.25 kilobyte storage in the controller for a 32 gigabyte DRAM memory. And if you do the calculation for having it per row, it's much, much higher. That's the idea. The second and the third is once you have these addresses of the rows stored in Bloom filters, memory controllers refreshes the rows in different bins at different rates. Basically, when it gets an address to refresh, the memory controller checks the bins. Should I refresh it at this point, or should I delay it until 256 milliseconds? Or what rate? Should I do it at? Should I use the rate that's? Which rate should I use to refresh this row? Is that clear? Can everybody hear me in the back, by the way? Okay, good. Okay, so how do you do the profiling? I will not go into this in detail, but basically someone needs to do it. The manufacturer can do it and expose it. The DIMM manufacturer can do it and expose it. Or maybe once you boot up your computer, you can figure it out. Or maybe you can do it online. Online is probably tough. But basically, to profile the retention time of a row, you need to write some data to the row, prevent it from being refreshed, and measure the time before the data gets corrupt. That's the idea. But you have to find the minimum retention time. And there are a couple of challenges that I will which are exposed in our recent ISCA paper this year. I'm not going to cover. And one is actually the data pattern that you write into a row determines the retention time. Data pattern, because that determines how much interference that happens between the different bit lines and the word lines. So that's important. The second is the phenomenon of variable retention time. It turns out there's a random process in which charge gets trapped in the access transistor, in the gate of the access transistor. As a result, the retention time, the rate at which the charge of the capacitor drains through the access transistor changes dramatically. And that's called trap-assisted gate-induced drain leakage. As a result, you get very different retention times for a given DRAM cell. So you have to figure out the lowest retention time in the presence of this effect. Let's assume that that can be done. Once you do this, we'll have to efficiently and scalably store the rows into retention time bins. Question is, how do you do that? So we use hardware Bloom filters. Is everyone familiar with Bloom filters? Yes? Who's not? Don't be shy. Okay, great. So I'll talk about Bloom filters then. This is actually a great data structure that's used for many different purposes in computer systems. It doesn't have to be hardware, but the properties of it make it amenable for implementation in hardware nicely. The idea of a Bloom filter is basically to represent a set. It represents set membership in a very compact manner. So the question is, you have some elements that are part of a set, and you'd like to be able to test quickly, is this element part of the set? That's what we're trying to do here, right? You have some rows that need to be refreshed every 64 milliseconds, and you put them in this data structure, and you'd like to test this data structure very quickly, and the data structure should tell you, yes, this element is part of the set. And Bloom filter enables that compact representation. Right? And it's approximate. It's not perfect. So you can sometimes get false positives. You can say, you can ask the Bloom filter, is this element that I inserted to you previously in the set. The balloon filter will always tell you, if you had inserted it into the balloon filter will always tell you that, yes, it is. So there's no false negative. But you may have inserted not have inserted an element, and if you later test the balloon filter may tell you, yes, it is in the set, which means that you get a false negative, right? Oh, you get a false positive. So I'll illustrate with this. So how do you actually do set membership? One option is to have a bit associated with each row, right? You can have a huge bit vector that's set to 1 if the row is in the bin, and it's set to 0 if the row is not in the bin. But that's a huge bit vector. So we're going to make a bit vector that's much smaller, but we're going to hash the addresses into that bit vector. That's the idea with the balloon filter. Instead of having a bit vector that has 1 bit element for each potential element, we're going to have smaller bit vector, and we're going to hash the addresses into that. So this is our bit vector. Basically, let's say we want to insert row 1. Basically, we have multiple hash functions. If you want to insert row 1, you take row 1's address, you go through the hash functions, and these hash functions map to different bits in the bit vector, and you basically set those bits. And the fact that those bits are set mean that all elements that map to those bits are inserted. So row 1 is inserted this way into the balloon filter. So how do you check whether row 1 is present? Basically, later on, the memory controller sends row 1's address. It goes through these hash functions, and it discovers that all of the bits that the hash functions point out are set. As a result, the balloon filter says, yes, row 1 is present. Let's insert row 2. Well, let's actually check whether row 2 is present. Basically, row 2, you take the address, you go through the hash functions, and they map to some bits. And one of the bits happened to be 1, but the other bits happen to be 0, which means that row 2 shouldn't have been inserted. As a result, the balloon filter says no. Now let's insert row 4. You take row 4's address, you go through these hash functions, they map to some bits, and these bits are set to 1. Now let's check if row 5 is present. Remember, we didn't insert row 5. We inserted only row 1 and row 4 so far. This row 5 goes to these hash functions, the address, and the result of the hash functions happen to map to bits that are already set, even though we never inserted row 5, right? As a result, the balloon filter says, yes, row 5 is here. I have row 5 in my membership, right? But this is not true. This is called a false positive, right? But this is actually okay for our purposes, right? False positive means that, for our purposes, a row may be declared present in the balloon filter even though we didn't insert it. Which means that we're actually refreshing this row more frequently than it's needed, which is also fine, right? Because we were refreshing everything at 64 milliseconds anyway. So it's not a problem. The advantage of a balloon filter, and you can apply balloon filter when you don't want to have false negatives, right? Rows are never refreshed less frequently than needed. There are no correctness problems, right? Basically, the balloon filter will not tell you that something is present if you didn't insert into the balloon filter. And this is a scalable data structure. One other option is to have actually a table that stores the addresses. You might want to ask, we have only 1,000 addresses, row addresses that we need to store. Why don't we design a table and put it in the memory controller? And the memory controller searches that table every time it needs to issue a refresh. Now, that's a reasonable design option. The downside is a content addressable memory. That's the first problem. But the second problem is, what if you add more memory into your system, into your memory controller? Now you need to increase the size of that table, right? And you need to basically have a worst-case table size, which is not necessarily efficient. A balloon filter, on the other hand, you could keep inserting things to it. It never overflows. Basically, it always insert things, and the false positive rate increases, but you still get correctness. And this is also efficient. Basically, you don't need to store information on a per row basis. As a result, you get simple hardware. So you get 1.25 kilobytes for 2 filters for a 32 gigabyte DRAM system. Okay, so once you have this, how does the refresh controller, memory controller function? Basically, choose a refresh candidate row. It determines which bin the row is in by checking the balloon filters, and determines if refreshing is needed. And this is the algorithm. I will not go into the detail, but you can guess the idea, basically. You choose a refresh candidate row, you check the balloon filters, and if it's not in any of the balloon filters, basically you refresh it every 4th 64 millisecond window. If it's actually within the balloon filter that says you should refresh it every 64 milliseconds, you refresh it right away. So because most rows are not in these balloon filters, most rows fall into this category, you can reduce the refresh rate by 4x. So how do you tolerate temperature changes? Very quickly, because this question was actually asked. This is actually a known thing, and actually our ISCA paper quantifies the effect of temperature on retention time. It's very predictable. And this is what people have figured out as well. Basically, you have a change in temperature causes the retention time of all cells to shift by a uniform and predictable factor. And you can scale the refresh rate based on that uniform and predictable factor. And today, low-power DDR controllers actually do this. Today, you have the scaling that happens in LPDDR systems. So where do you implement this is another question. I'll go over this very quickly also. The baseline design, as I told you, refresh control today is over here in DRAM. Radar can be implemented either here or here. Regardless, you have to change this interface. You cannot do it without an interface change over here. Basically, you can put radar over here. You can have the balloon filters over here, and the memory controller specifies when to refresh each row. Or, in this case, this is the additional overhead, and you can read the paper for that. Or you can put radar over here into the DRAM, and when the memory controller issues an auto refresh command, the memory controller doesn't know which rows are being refreshed, but the DRAM internally says, I'm going to refresh this only, and that's it, by looking at those balloon filters. So you could do it in either place. In either case, you have to change the interface somehow. Here, if you do it over here, now the auto refresh command needs to have variable latency, perhaps, right, if you want to optimize the system. Because now when the memory controller sends an auto refresh command, the DRAM may not be refreshing anything. Right. Okay. And the overhead is similar over here, but DRAM actually is much more cost constrained. So maybe a good design is actually doing it in the memory controller. Okay. Let me go briefly over the results so that we can cover some more ideas too, and I'll take some questions as well. But basically, we evaluated this with a 32 gigabyte DDR3 system with multi-core, and the baseline is 64 millisecond refresh interval. And this is the configuration of the radar. You can actually configure it with having more bins, right? You can actually add more bins. But you get diminishing returns because of the shape of the curve. Remember, as you add more bins, you need to store more rows into that bin. So with a variety of workloads, the refresh reduction is approximately 75%, as expected, because most rows need to be refreshed every 256 milliseconds, and you get some false positives. That's why you get the full. You don't get to 75%. This leads to 16% reduction in DRAM dynamic power and 20% reduction in DRAM idle power, and approximately 9% performance improvement with these workloads, because now refreshes do not get in the way of normal read and write accesses. Okay, you can read the paper for this. This is a comparison to some other mechanisms that are employed today or that were proposed. Just to give you an idea, this is what happens as you increase the memory intensity of the workloads. As you go from left to right, over here 0% to 100%, the access rate, how often the workload accesses memory increases. And this is the average across all those workloads. Y-axis shows the performance. And if you look at these numbers specify the performance improvement of radar compared to today's systems. As you increase the memory intensity of the workloads, the performance improvement of radar increases. Performance improvement of getting rid of refreshes increases. And this makes sense, right? Because as the workload becomes more memory intensive, refreshes get more in the way. As you increase the memory intensity, the energy benefit decrease. And this makes sense also because as you increase the memory intensity of the workload is doing a lot of activates and writes and reads, which are consuming a lot of energy, which means that refresh is a smaller fraction of the overall DRAM energy. So this is expected also. A little bit on scaling, I'll give you some numbers, but don't take all of these numbers with a grain of salt. Numbers, it's really the trends that actually show some interesting behavior over here. Basically, as you scale the capacity of DRAM, this is what happens to the performance of the baseline auto refresh and radar. So we were evaluating with these chips, but as you scale the capacity, using something like radar becomes much more important. The performance improvement is about 108% in this case. Again, take these with a grain of salt because we don't have 64 gigabit DRAM chips, but this is the scaling result that you get. This just shows that refresh will become a lot more important going into the future. And this is the energy savings that you get at 64 gigabit DRAM node. Basically, here we get about, I believe it was 16% energy savings. You get much more, 50% energy savings as if your DRAM is much larger. Okay? Any questions? Yes?
Couldn't you often tackle this on the operating system perspective? Because I think if you have this 1,000 rows from 60 million rows and you do some storage space and you just mark some of the rows as non-usable, it's page stable, should also be okay. And then way you could always refresh at the lowest rate.
Sure, you could actually do that also. I believe you could do that also. I think the solutions need to be added up, perhaps. That requires changes to the operating system and more communication. We're having trouble even getting that communication between the memory vendor and the memory controller. So now you have to communicate to the operating system and get them involved also. But I think once you do that, there will be another 1,000 rows that... So I think we can solve this problem. But that's a good idea, too. I agree. And maybe there are some other ideas that you will come up with that will make it even better.